Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. While at NeurIPS this past December, I attended the second annual Black in AI workshop, which gathered participants from all over the world to showcase their research, share experiences, and support one another. This week, I'm excited to continue our Black in AI series with this interview with Alvin Grissom II, Assistant Professor of Computer Science at Ursinus College. Alvin's research is focused on computational linguistics, and we begin with a brief chat about some of his prior work on verb prediction using reinforcement learning. We then dive into the paper he presented at the workshop, Pathologies of Neural Models Make Interpretations Difficult. We talk through some of the quote-unquote pathological behaviors he identified in the paper, how we can better understand the overconfidence of trained deep learning models in certain settings, and how we can improve model training with entropy regularization. We also touch on the parallel between his work and the work being done on adversarial examples by Ian Goodfellow and others. Enjoy. All right, everyone, I am on the line with Alvin Grissom II. Alvin is an assistant professor of computer science at Ursinus College. Alvin, welcome to This Week in Machine Learning and AI.
Thanks. It's good to be with you.
Absolutely. It was really great meeting you at the recent NeurIPS conference, and in particular, the Black in AI workshop where you presented the paper that we'll be talking about today, Pathologies of Neural Models Makes Interpretations Difficult. But before we jump into that, I would love to hear a little bit about your background and how you ended up doing research at the intersection of computational linguistics and machine learning.
Sure. So I have a kind of winding path. So as an undergraduate, I was actually very interested in AI, and this was before it sort of blew up into what it has recently become. And I was always interested in language as well, just in general, even before I was in college. And actually, not a lot of people know this about me, but I considered becoming an English teacher when I was in high school.
Oh, wow.
So that didn't happen. When I was a master's student, I was getting a master's in computer science, and I was doing language processing stuff. My thesis was on actually some sentiment analysis, like qualitative and quantitative analysis of sentiment in Japanese. So I really enjoyed doing that, although I'm not sure I'd want to go back and read my master's thesis at this point. After that, I was actually a PhD student for a year in linguistics. Decided that wasn't really for me, at least at that time. And eventually I worked for a year, and then I went back into sort of the computational linguistics area, and that's where I am now. So many years later.
Awesome. And I'm curious about the decision. Was that a decision that linguistics wasn't for you, but computational linguistics was, or was it just the timing around the PhD?
Well, it wasn't the timing. I think there were a lot of things going on. I'm not sure how deeply I want to go down this rabbit hole, but there are some contentious issues in linguistics, and I didn't realize this at the time. I had some sense of it, but there are a lot of things going on, but I still am very interested in linguistics, but I wanted to get kind of a broader view, and it was more satisfying, or at least maybe satisfying isn't the word, but more, it was easier. I felt better about the intellectual claims I was making I could make in computational linguistics than I did in some of the linguistic stuff I was interested in. And I say this with some trepidation because I don't want it to be misinterpreted as saying linguistics isn't real. Or I'm not saying that. I'm just saying that for me personally, and maybe it's just because of my background, but there are some other epistemological reasons I found the computational approach to be more to my liking for a PhD. if I'm going to study something for 5+ years, I want to be comfortable with it. And I found that I personally wasn't.
Yeah, linguistics is one of those fields that I've done some kind of cursory reading of, and I find it fascinating. And so when you said that, I kind of got the sense that there was something there that was kind of interesting. So thank you for elaborating on that.
Sure. I mean, actually, it's funny because a lot of the things that bothered me at the time don't bother me so much anymore. But I had to kind of get some distance from it, I think, because I was kind of in fight or flight mode for a whole year when dealing with a lot of that, and then I got away from it and was able to more leisurely sort of think about the issues, and now I'm not so perturbed anymore. But at the time, I was not a happy person. So,
Okay.
yeah.
Okay. So then your research more recently is focused on the computational side, as we've discussed. Can you elaborate on the kinds of things you've been looking at?
My PhD work, which so I finished my PhD in 2017, and I've continued to extend that a little bit, and so that's on simultaneous interpretation. So trying to make computers do simultaneous interpretation. Like at the UN or something, someone's speaking in one language, and you want to translate that in real time without necessarily waiting for the whole sentence to be uttered. Just because that problem is so easy, of course, I'm being sarcastic. We wanted to do this for what are called SOV or subject object verb languages, to subject verb object languages. So a language like Japanese, for example, the verb comes at the end, but in English it comes after the subject. So if you want to translate, I to the store went, you have to wait until you see went at the end of the sentence before you can say I went to the store.
Mm-hmm.
So that's a problem. And so
It's a problem for humans too, right?
it is a problem for humans. So one of the things, we had to ask ourselves was, how do humans do this? And they do a lot of things. So they'll reorder sentences, they'll use more vague words sometimes. But the first approach we sort of looked at, and which I'm still working on with some other people, is predicting those verbs. So humans are when they do this, it's actually very cognitively taxing, and they can only do it for so long at one time.
I've noticed that at events that the transcriptionists kind of work in teams and they'll swap off every
Mhm.
half an hour or hour or something like that. And I've had people tell me it's because it gets really taxing for them.
Yeah, it's really. I mean, if you just think about what they're doing, right? They're processing two languages simultaneously, translating between them, and predicting
Mm-hmm.
the future, essentially. And your brain can only take so much for that long. And so what I worked on, one of the things was trying to see how computers could do this. And so it's like, well, let's see if we can predict these verbs, which in terms, like in Japanese, let's see if we can predict the final verb and then just put it in the sentence earlier. It turns out that's very difficult. But we worked on that, and we used what's called reinforcement learning to try to teach a system. We were actually the first people to do this. Some other people have done it before, since then, with neural networks and other things. But um, let's see if we can learn under which situations we can trust these predictions. So you have like a prediction of the verb, you have like a translation, and let's see, when should we trust each, and what should we do with that information. And so this sort of spawned this other project, which has taken on a life of its own, which is just verb prediction and predicting that kind of stuff incrementally, which it turns out is a very interesting problem, both for psycholinguistics and for machine learning and computer science. And so since then, I've worked on some other stuff, but the paper you brought up was the pathologies of neural models make interpretations difficult. And so that looks at.
Actually, if you don't mind me hitting
Sure,
pause.
sure. Yeah, I
you,
know I'm going pretty fast.
no, you touched on something that is potentially interesting. This use of reinforcement learning as part of this verb prediction problem. So it sounds like you made a distinction between reinforcement learning and folks that came along after and did deep reinforcement learning. You were using more traditional RL methods.
Right, we were using imitation learning. Yeah.
Okay. And so can you walk us through kind of how you formulated the problem there and how you applied RL and imitation learning to that particular problem?
Sure. Yeah. So you can think of a sentence. So we don't speak sentences all at once. We speak them. You could say a word at a time, although defining word in some languages can be difficult. But we speak them incrementally, and you can think of that as like a time series of steps. So if you kind of discretize the sentence by word, say, then every time that so imagine you're or an interpreter. So you can imagine that every time you hear a word, you have a decision to make. Okay. And so what should that decision be? So you might want to do nothing because you might not be certain and enough. You might not know enough, like to make a good to say anything or to make a translation, an incremental translation. So you might just wait, or you might make the best translation you can with what you have. You might make the best translation you can with what you have while making some kind of prediction. So maybe you have a good idea of what the next word is or what the verb is or something like that. And so in a reinforcement learning framework, you typically have some kind of time series of steps. And every time you take a step, you choose an action. So in our case, the actions were things like wait, which means don't try to translate anything at that point. Commit, which just means that you make the best translation of that fragment you can at that point. Verb, which does the same with the verb prediction, and we had another one for the next word that does the same thing. And so that in that formulation, every time you get a word, you just choose an action. And if you have some examples of good actions, this is where the imitation learning comes in. Then you just try to imitate the good examples and try to generalize from those good examples when you can take what action.
How were you training the model? Were you training it on kind of existing translation, some corpus of translated, phrases or documents or something like that?
Right. We were using a standard like web corpus of parallel data. So it's not ideal because it's not actual simultaneously translated data, which there's another paper by He that and others that shows that these look very different. So that's a weakness in it, but it's also just because that data doesn't really exist in large measure. There's some, but it's not enough to really train a model in the traditional way. So yeah, we were using basic parallel data.
Okay. It strikes me that actual simultaneously translated data would be, there's a noise aspect to it because the translators are making these mistakes that, they might not make if they had full access to full information. Is that
exactly? Yeah,
a factor
that's a problem. I don't know if it's a problem or not, but it's definitely an aspect of the data. So there's actually some interesting data where they have three translators. I think it's Japanese to English. Three translators of different, I guess you could say, experience levels or ranks, and and they have them all translating the same stuff simultaneously, and you can actually see like the different kinds of things that they do and strategies they use and mistakes they make and stuff like that. It's pretty interesting.
Huh. Wow. Interesting. You were starting to introduce the paper that I saw you present, the Pathologies paper. Can you tell us a little bit about the background and motivation of that paper?
Yeah, so there's been an uptick in interest, well, obviously in deep learning in general. I mean, everybody knows that, and who's going to be listening to this podcast. But one of the criticisms of deep models is that they're black boxes. So if you have like a logistic regression or something of some kind of linear model, you can look at the weights, and even though that's not a perfect method of analyzing a model, you can get a sense of why the model is making the decisions it's making, right? But with a deep model, it's very difficult, right? And the deeper and more complex the architecture, the harder it gets to interpret what these models are doing and why. And so, because we want to interpret these models, we thought, well, let's look at what they're doing. And so, what we found is that they exhibit what we call these pathological behaviors. So they don't do what any reasonable person would expect they would do when they're given something that they're not used to seeing. So I think the example I used in the presentation was you can reduce, so for question answering, like you can reduce the question to just the word did, right? And not only, so it still gives the right answer, but the confidence in the right answer goes up if to like 91% if you just ask did, right? Which is a ridiculous, yeah.
So I found that the example really interesting. Let's walk through that in a little bit more detail. It was well, let's go back to the data set. The data set is question answering. Was it squad?
It was squad, yeah, for that one.
Okay, and so tell us about what you were trying to do with a given example from the squad data set.
Right. So you're given some context, like some kind of short sequence of sentences with some information, and you give it a question, and you want the model to give you an answer to the question based on the context. And intuitively, you want the final confidence of the model to reflect the value, like sort of the value of the information in the question, right? So, like if I ask you, so if I give you a paragraph to read and I asked you, what or something, right? So you have no idea what I'm asking, right? You wouldn't say, yeah, I'm 91% confident that, the answer is X. But we found out that these models actually do this a lot, so we wanted to, systematically show that this is like a systemic problem in some of these models.
Okay, and so how did you go about showing that?
So we would incrementally remove words from. So for squad, for example, we would incrementally remove words and just observe, so without changing the answer actually, and observe how the confidence shifted and what we found is that it doesn't really comport with what humans. So we also did some human experiments to verify this, but it doesn't really comport with what a human would expect, and nor does the human performance reflect necessarily what the models do under these circumstances.
And so the words that you're removing are from the context passage or from the answer?
From the question.
Or the question rather.
Yes.
Right,
yes.
right. So you've got these three pieces. Then you've got the kind of the sequence of sentences. That's the context. You've got the question and the answer. And so you're removing words from the question, and you're trying to see the way that changes the prediction of the confidence level in predicting the answer. Is that the right way to think about it?
Right. That's right. Yes.
And then, if I'm remembering this correctly, you would kind of sequence the words that you removed by. Were you sequencing on the one that was most likely or had like the least information or the most information or something like that?
Right. So we remove what we call the unimportant words. So we want to remove the words without changing the answer.
You were removing the words that minimize the changing confidence of the answer. And then I'm trying to remember you showed a sequence of the words that you removed, and I guess what was strange about it is that oftentimes you were removing words that as a human you would think had the most meaning in the question, and you ended up with this, just like a question word.
Right.
I'm trying to capture like the visual on the podcast, which is sometimes hard to do, but it was really interesting to see the way that evolved on that slide.
Yeah. So that was one of the sort of pathological behaviors, right? So what it doesn't. So nothing that I don't want to say nothing we did, but a lot of what we did just doesn't, doesn't go with what we would expect, right? So what the
Mhm.
model thinks is an important term might not necessarily be what a human would consider an important term.
Did you end up in this paper taxonomizing these pathological behaviors? Are there, do they, are there, how many of them are there? Are there names, or is it more exploring kind of this one particular one that we've been discussing?
It was more exploratory. I mean, so we did have a section. So we talked about model overconfidence, which is one problem, right? And I'm trying to think, did we give these names? I don't think we named the pathologies. I think we just sort of just described them.
And so one of them is this overconfidence. What are some of the other ones that you tended to see?
Right. So I think rather than I think a different way of thinking about it is that so we tried this on a number of different tasks. So the way we so the method that we used was sort of this word removal, right? And we did this for squad, we did this for visual question answering, and we did this for SNLI, which looks for things like contradictions and things like that. And we noticed, and we showed the same sort of the same kinds of pathologies on all of these different tasks when by using input reduction.
Okay. So you kind of the same idea of successively removing words, and you ended up in the same kind of weird part where you're left with words that wouldn't be the most useful ones that you would expect.
Right, right,
And so,
right with the confidence not necessarily being what you would expect either. Yeah.
right, right. And so what did all this tell you about neural network models and trying to interpret them?
That it's difficult. Which is in the title, right? So I mean, it's not necessarily surprising. So there's been some previous work that has shown similar things for especially sort of images. There's this notion of like rubbish examples where you show what looks like random noise, and the classifier whatever gives you 90% confidence that it's a flower or something. And so this is this is definitely related to that. And so we also, proposed a method of trying to mitigate this using a kind of regularization on the by training on the reduced inputs. But yeah, I mean, I think we're not just trying to say that deep learning models are garbage or whatever. We're just trying to identify sort of the shortcomings and understanding them so that we can try to address that.
Right. And did the regularization approach that you tried, I'm presuming that worked to some extent?
It did. So the nice thing about it is that we were able to use this to with almost no change in accuracy. So we were able to get a more reasonable distribution of confidences that looks more like what a human would expect without really hurting accuracy.
Okay.
So even even though the model itself is still difficult to interpret, there is a way of training it that gives you, I guess you could say, more interpretable confidences at the end of the prediction.
Is it this specific approach to regularization, the one that you tried, that you found to have the advantage of, let's say correcting these models in this way? Or is it regularization in general, in trying to force the networks to generalize more that, had some kind of general improvement?
Right. So I don't know that we tried dropout or something like that. I guess I could ask the other people who are working on this. But we just showed that this particular form of regularization helps. It's possible. I mean, I doubt it would hurt. I mean, I don't know. But to use some other kind of regularization, if you want to call it dropout regularization. But yeah, in our paper, we just showed this particular method works.
What have you done kind of in this direction since then? Or where do you, how would you see extending this kind of work?
Yeah, so I personally haven't extended this since last month or whenever we published this. I guess it was maybe it was 2 months ago. But there is another paper, a workshop paper by an undergraduate student at the University of Maryland named Eric Wallace that is attempting to do something similar. I think he's using k-nearest neighbors so he was also the second author on this paper to try to. So I haven't read his paper, I have to confess, but I think he's trying to do that to do something similar to try to mitigate, make these models more interpretable.
Maybe tell me a little bit about how this particular paper fits into kind of your broader research agenda nowadays.
Sure. So going back to verb prediction a little bit. So in 2016, I published this paper on verb prediction in Japanese and German, mostly Japanese. And that was using just linear models. And so I'm also interested in psycholinguistics. So I was interested in sort of comparing the features that model was using to make its verb predictions to what humans seem to be using to make the same predictions, right? So we always try to, I use the word we loosely, but some people try to make these kinds of analogies between machine learning models and humans, but without actually looking at what the model is doing, it's not clear that that is justified. So as we're moving to these, as we have moved to more deep learning methods, I think if you want to make claims about a model, for example, informing something about what a human is doing, I think it's helpful to have some sense of what the model is actually doing internally. So on that verb prediction project, for example, I just looked at the weights of the model and and tried to look at how adding certain features that were linguistically interesting affected the predictions. And you can also do that with a deep model. You can also look at something like attention weights, those kinds of things. So I guess what I'm pushing here is, accuracy on a data set is an important metric to look at, but it's not the only metric. It's not all we care about. If we're doing scientific inquiry, then we want to look at the model itself. We want to understand why the model is doing what it's doing to the best that we can. Which is not to say that accuracy isn't important, but as someone who's interested also in linguistic questions, it's much more satisfying scientifically if we can peek inside the models and see what they're doing. And if we can't, to at least be able to have some sense of why we can't, if that makes sense.
What's your sense of the kind of relationship between psycholinguistics and the kind of work that's happening on the machine learning and deep learning side? Have there been any interesting kind of cross pollinations or cross results there?
There have, and for quite some time, I think. So I think there's so much potential that's only beginning to be, the surface of which is only beginning to be scratched. So, for example, there's a whole, area of neuroscience of language where we have these really interesting experiments where you give a person a stimulus of some sentences or words or something, and you give them an EEG helmet or you take an fMRI, and you see how their brain is responding to these stimuli. So I think that's it's an incredible treasure trove of potential machine learning research, and so it's starting to be done. It's been done for a few years by some people. So for example, if you wear an EEG helmet, your brain produces certain. For simplicity, I'll call them brain waves, but it produces a graph that's called an ERP, event-related potential. And I think it's really interesting question. So, what can you predict by looking at an ERP? Can you predict other aspects of that person's linguistic performance based on looking at these kinds of things? But even outside of sort of neuroscience, which requires a more specialized background, arguably, For my verb prediction work, I looked at what are called case markers in Japanese, and it turns out that both the classifier, the model that we built, and the humans, there's previous research that shows that humans also do this. We're using these case markers in Japanese to predict verbs. And so that was an instance where it looked like the model and the humans were using the same information in an interesting way. And so I think there's a lot of potential there for example, you might look at a model and think to test whether what the humans are doing is related to what the model is doing, or vice versa. So I think there's a lot of potential there.
Awesome. Besides the paper that we've been discussing here, or that we discussed previously here, are there any interesting references that you would point someone to who's interested in exploring this area more deeply?
Sure. So the one that there's a lot. I'm not going to be able to name them off the top of my head, but one that comes to mind is the paper on rubbish examples. So if you just Google rubbish examples, I think it'll deep learning rubbish examples, I think it'll come up. So I think that's probably, at least that's coming to my mind right now, the most related paper, and that was published quite a bit before ours, and that's more related to visual tasks, I think, than linguistic tasks, but it's a similar idea, and was certainly part of the inspiration for our work.
Okay, awesome.
Yeah.
Awesome.
Yeah.
Well, Alvin, thank you so much for taking the time to chat with us.
Sure. Thank you very much for having me.
All right, everyone, that's our show for today. For more information on Alvin or any of the topics covered in this show, visit twimlai.com/talk/229. For more information on our Black in AI series, visit twimlai.com/blackinai19. As always, thanks so much for listening, and catch you next time.